Good afternoon, all. Let's proceed to our next invited talk. Our next speaker is Francois Sarrazin. The title of the talk is Antenna Radiation Efficiency Measurement within Reverberation Chamber. A warm welcome to you, sir. Now, I would like to hand over the platform to distinguished chair for this session, Professor Abdullah P. from CUSAT. I welcome you, sir.
Okay, thank you. Can you hear me?
Yes.
Okay.
Yes.
Thank you for giving me this opportunity. So we are going to start the afternoon session by the invited talk on antenna radiation efficiency measurement within reverberation chamber. We have with us Dr. Francois Sarrazin, who received the MS degree in electronics and electrical engineering from Polytechnique Nantes in the year 2010, and the PhD degree from the Institute of Electronics and Telecommunications of Rennes, University of Rennes 1 in the year 2013. In 2014, he worked as a postdoctorate fellow at the Royal Military College of Canada in Kingston, Ontario. And from 2010 to 2014, his research was focused on antenna characterization using the singularity expansion method applied to both in the time and the spatial domains. In 2015, he worked as a research engineer at the CELF Grenoble on electrically small frequency agile antenna and radiation efficiency optimization. Since September 2016, he is an associate professor at the University Gustave Eiffel and ECYCOM laboratory. His research activities include reverberation chamber characterization and miniature antenna measurement. And over to you, Dr. Francois.
Okay. Thank you, Mr. Chairman. Good morning, everyone, or good afternoon, maybe Indian time. So as it's been said, my name is Francois Sarrazin, and I work at APSYM nearby Paris. So this talk today is about antenna radiation efficiency measurements within reverberation chamber. So it's a mix between a tutorial talk with some basics about radiation efficiency and then some technical study with reverberation chamber measurements. So first of all, I would like to thank Dipti for this kind invitation. And it's actually a shame that this conference doesn't happen in real in Cochin, but still good to have it online at least. I would like also to thank people that have been part of this work. So from IETR, Philippe Beignet and Jérôme Sol, and from my own laboratory, Elodie Richalot, which is full professor I work with, and Wafa Kruka, a PhD student. So quickly, where I come from. So APSYM laboratory is so nearby Paris. Basically, we like to say it's between the Eiffel Tower and Disney World. So that's where we are, right in the middle here. So it's about 20 kilometers from Paris, in the countryside, let's say. And we are about 75 people, half associate professor, full professor, and half of students, basically. So mostly PhD students. So we actually recently merged, like the Université Gustave Eiffel has actually been created in 2020. So that's a very new university. So the former university I was in is the Université Paris-Marne-la-Vallée. And it merged with 6 other institutes or engineer school in the same campus. And our new name now is Université Gustave Eiffel. It is part of this merging is part of investment for future in France. And the leitmotif of this new university is to inventing the city of tomorrow. So basically, our main targeted application is regarding smart cities and small connected objects. So all these objects regarding antenna domain, it's mainly small sensors that are, so including miniature antenna, that are embedded or buried in lossy medium, for example, in pavements or in concrete in the buildings, or you have also applications in body area networks where sensors are implanted into a human body. So all of this made huge constraints on the antenna design, and especially one specific parameter, the radiation efficiency. Okay, so this is the outline of my presentation. So the first part is dedicated to general aspects about the antenna radiation efficiency. So it starts from the basic definition and then asking why measuring it, because it's not always a parameter that is very that's not always important. Like nobody, not everyone look at it very carefully. So it's a why do I want to measure it actually, and how to do it. Let's say the classical way. And then the second part will be about reverberation chamber. So I use this chamber to measure radiation efficiency, but I will first introduce it. What is it? It's quite new, let's say, in the antenna domain. So introduction, how to measure radiation efficiency, and then a technical study about the steering effects on the estimated radiation efficiency. Okay, so let's say it's a mix between tutorial and technical presentation. So if I go back to the basics, the antenna radiation efficiency, how to define it. So first here is the equivalent circuit of a generator on the left and the antenna input impedance on the right. So the generator will generate a power PG, and due to mismatching and so impedance mismatching, some of this power will go to the antenna. So I call it the incident power, that power that actually arrives to the antenna, and some of them will actually reflect on the antenna due to mismatching, and it will be some loss into the system. So what is actually going to the antenna, the incident power, is defined as PG times 1 minus gamma square. And of course, gamma, you can compute it thanks to this very known equation from theory's line theory. And please don't forget the conjugate here when you are dealing with complex characteristic impedance. Okay, so some of the power actually arrive to the antenna, but not all the power will actually radiate. So there is a second radiation loss process due to the radiation efficiency. Here, the incident power that arise on the antenna, most of it or some of it will actually become the radiated power, so radiate into free space and become available to a receptor. But some of them will also get lost into the antenna itself. So these are not lost due to mismatching that have already been taken into account here, but these are lost due to the antenna itself. That's an object with limited conductivity, some dielectric, and it will induce some losses inside the object. So the radiation power will be the incident power times the radiation efficiency. Okay, so there is always two losses mechanisms, one related to mismatch, impedance mismatch, and one related to the radiation efficiency. So how the incident power is actually radiated by the antenna. So if I go back to the equivalent circuit, if I want to distinguish between this radiation efficiency and mismatch, then I have to divide the complex impedance into three components. So the imaginary part, that stay as is, but the resistance can be divided into two resistances, the radiation resistance and the loss resistance. And so the radiation efficiency can also be defined as a ratio of the resistance of the input impedance, antenna input impedance. Okay, and before I go on the why measuring it, I just want to recall some terminology. That's always something I highlight, that I stress out when I do courses on radiation efficiency. So radiation efficiency is only due to the ohmic losses and the dielectric losses on the antenna itself. So sometimes in the balance, for example, you can divide it, radiation efficiency, as a product between the efficiency due to ohmic losses and the efficiency due to dielectric losses. So it's a combination of the two. In practice, it's barely measured. Like one of these components is quite hard to distinguish between these two efficiency. So it's almost never actually achieved. So one look generally at the radiation efficiency as a combination of the two. So from this efficiency, radiation one, you can also name the total efficiency that includes, both the mismatch, so the reflection coefficient, and the radiation efficiency. And so the total efficiency is defined as 1 minus gamma squared times the radiation efficiency. So these two terminology are quite close. Okay, it's efficiency, but it's not the same. So it's not always stressed out on technical sheet, for example. We just talk about efficiency, but it's very important to distinguish between the two of them. And in the same manner, you can define the gain as a product between the efficiency and directivity, which is very famous. But sometimes you also hear about the realized gain that include the mismatch here. Okay, so it's the total efficiency times the directivity. So all of this is very well defined in antenna book, but it's not always very highlighted somewhere, especially due to the particular case of a radiation efficiency that is not always very important to take into account. Okay, so it was a very quick review of the basics. How is it defined, the radiation efficiency? And now I will go to why do I want to measure it? It's not straightforward, but we want to measure it. And why is it so? Here is a curve of the radiation efficiency as a function of a frequency for a given antenna of a given size. So basically, when you work with lambda over 2 or even lambda over 4 antenna, you are in this region where the radiation efficiency is very high. So I said 90%, could be 95. It's usually very high. So in that case, you know it's very high. It's not very important, but it's not much you can do about it. It's 95%, 90%, that's good, and you let it this way. And if we look at the total efficiency that appears here, it comes the curve in red. And so the total efficiency will be, if it perfectly match at this frequency, that you get a curve like this. So it gets very high at some points and then decrease on both sides. But now if you start dealing with miniature antenna or electrically small antenna, then you will obviously, as the curve says, lower the maximum radiation efficiency that you can achieve. So for lambda over 10, it's usually a bit decrease, although it is not very hard. But once you go smaller than that, then for example, lambda over 15, then the radiation efficiency will be, for example, 50%. So you can match the antenna the way you want. Even if it's perfectly matched, you already have half of the power that is lost due to radiation efficiency. So this is in this area where the antenna is electrically small, where the radiation efficiency becomes very important to take into account. So in the miniature antenna design, there is a classical trade-off that is highlighted between the size, the bandwidth, and the efficiency. So here we see that for a given size, if you reduce the frequency, then the antenna becomes electrically small and the efficiency decreases. And so overall, if we look at the fundamental limitation of antennas that has been first derived by Shu in middle of the previous century, the size is proportional to the ratio between the radiation efficiency and the Q factor. The antenna Q factor here is inversely proportional to the bandwidth. So the size will be proportional to the product between radiation efficiency and bandwidth. So for a given size, if you want to improve the radiation efficiency, then you will lower the bandwidth, and vice versa, of course. So in general, you need a certain bandwidth. Like for application, you need 20 megahertz, 30 megahertz of bandwidth to achieve the capabilities of a communication. The size might be a strong constraint as well, as you want to integrate your antenna into a material. And so the radiation efficiency, then there is not much you can do about it. But it will obviously decrease as the size goes down. So that's why I'm interested into this parameter. And to highlight this trade-off that I just talked about, I show you a study that we've made a couple years ago. So this antenna works at 433 megahertz. Its overall size is lambda over 28, like the radius of the antenna. So that's a balanced antenna. So here, like a dipole-like antenna. So we feed it with twin cables, both with the connectors at the end, so that we measure the S parameter like a matrix 2 by 2, and then we deduce the S parameters as if it was an unbalanced antenna. So this measurement setup is made so that we don't disturb the balanced behavior of the antenna. So it is miniature because like the dipole has been folded, and then we add a capacitive at the end of a thin wire, and there's a shortcut here, like a PFA antenna, to do the matching. Okay, so this antenna is well matched at this frequency, 433 megahertz. Okay, and now our objective was to optimize the radiation efficiency. Okay, so to play with the resistance loss of the antenna, we actually modify the strip width. So we did a strip width optimization. We modify the strip width, so from 0.6 millimeter to 4 millimeter, basically. And every time to adjust the frequency so that it always resonates at the same one, we modify the length of the capacitor at the end so that it always resonates at the same frequency. And we perform simulation and also some measurements of the radiation efficiency that we obtain. Here are the results. So the radiation efficiency here as a function of the strip width in millimeters. We can see that if we enlarge the strip width, radiation efficiency will increase. Although we can see that starting from here, it doesn't change that much. But still, we can modify it from 18% to 50%. Okay, so we did good job regarding the radiation efficiency improvement. But in the same time, if we look at the Q factor, it also increases, meaning the bandwidth is decreasing. Okay, so indeed, we optimize the radiation efficiency, but in the same time, the bandwidth was actually decreasing. So this study highlights quite well the trade-off that we have to do when dealing with miniature antenna. So if you want to achieve a certain bandwidth, then you will have to take care of the radiation efficiency, but it doesn't become too low. Okay, so now how to measure it? So how do we measure the radiation efficiency? Let's say in the classical way, like the mostly used method to measure the radiation efficiency. I think it is the gain integration technique. So these techniques, the classic one, takes place in an anechoic chamber. So here you have a reference antenna or a transmitting antenna that radiates towards the AUT, so the antenna under test that you want to measure. And if you want to obtain the radiation efficiency, you have to measure a full 3D pattern of a gain. So you have to measure the 3D pattern of the AUT and then do a reference measurements to obtain the gain, so that you, in the end, get the 3D pattern of the gain of the IUT. And if you get this pattern, you will know that the gain, as I said earlier, is equal to the radiation efficiency times directivity. And so if you integrate it over the sphere, so that you have a full 3D pattern, so you can integrate the gain that you measured over a sphere. Obviously, the directivity, if you integrate it, it comes to 1. So what you obtain here is only the radiation efficiency. Okay, so this works very well. This is very well used. It has been used for 50 years or more than that, and it works well. However, it's really time consuming because you need to measure the 3D pattern. So you do one cut plane, second cut plane, and how many planes you actually measure. It's very hard to get a full 3D pattern. So obviously, you will limit the number of cuts that you perform. Usually 2 cuts, like H plane, E plane, you do 2 cut measurements and you integrate it and you assume that it's almost okay. Also, when you want to rotate it, sometimes you need a human intervention. So you come into the room, you modify the antenna, the axis of rotation, and you perform another measurements. So obviously, the phase sensor of the antenna might shift a bit as well during this process. And there is some alignment constraints. Indeed, when you deal with miniature antenna, as I said, phase center, if you move it like a few millimeters, one way or the other, it will modify it quite big. Sorry, it will modify what you obtain. So it's not very easy to perform, and it's not always the most accurate as you do a limited cut planes, limited number of cut planes. So my idea is to work on an alternative reverberation chamber. So it's brief recall of what is it and how the steering process occur within the cavity. Then I will introduce the radiation efficiency measurements. So the method itself that is used to measure radiation efficiency. And finally, a quick but more technical study about the steering effect on the radiation efficiency. Means how the steering that you perform within the cavity will impact the estimated radiation efficiency within the cavity. Okay, first introduction. A mode-steered reverberation chamber is basically an oversized parallelepiped metallic cavity. So it's a Faraday cage, a huge one, a big one, look big compared to the wavelength, of course, so that the modes can, the wave can freely radiate within the cavity. So we have a transmitting antenna here that is usually oriented toward the walls or toward the stereo itself, that is used to excite the cavity modes. So if you are working high in frequency compared to the size of the reverberation chamber, then there is a lot of modes that can be excited, and all the RC measurements are based on this property. So in order to modify the boundary condition within the cavity, we have a rotating metallic mode steerer. So this is represented here. So it's something that rotates over an axis of rotation. And so it modifies the boundary condition so that the field distributions within the cavity will change every time you move the steerer. Okay, and then there is what we call the working volume, which is represented in gray in this figure. The working volume, it is the volume far enough from the walls so that the boundary condition doesn't affect the statistical properties of the field. And usually the device under test is placed within this working volume. And the hypothesis that you make is that the fields are statistically, it means if you do an average over a stereo rotation, the fields are isotropic, spatially uniform, and spectrally uniform. It means that over a stereo rotation, you can assume that the field that arrive, that is incoming onto this receiving antenna or any device under test, come from all directions, so isotropic, is spatially uniform, so you can move your antenna anywhere within the working volume, you will get the same thing, and spectrally uniform, so it's the same as a function of frequency. Okay, so the first thing that you can mention here is that there is no rotation of the IUT that is needed. In fact, the incoming field is already coming from all directions. So you don't need to rotate it to get something that is integrated above the whole sphere. So it's usually a faster and faster measurements, and there is no human handling necessary on the antenna itself. Okay. So I will say a few words about the steering process, so the mechanical one. When you look at a Faraday cage, like a parallelepiped cavity, metallic cavity, if you look at the field inside, it's very regular, of course. There is a regular field distributions, so depending on the modes that we are looking at, and you obtain some field distribution like this. Once you include a mode steerer, then there is some random paths that occur within the cavity, and so the field distribution is much more random. But still, there is maximum and minimum depending on the spatial position. And so once you make this steerer move, this field distribution will change as well, but still randomized thanks to the complex shape of the steerer. And finally, when you average it, you will get something that is spatially uniform, because all this field distribution will always be random. And when you average all of them, you will get something that is uniform. So that's why we use such a mode steerer, to get our spatial uniformity. And so the goal of a steering process is to obtain several uncorrelated field distributions. Indeed, if you move only a very small steerer, then you will change the distribution, but only slightly, and it will be very correlated to the previous position. So the goal of a steerer is to get uncorrelated field distributions. And that's thanks to this uncorrelation that you will actually get a nice uniform average field. So to see this in a way, here is the reflection coefficient of an antenna measured within the reverberation chamber. So it's an antenna that is matched between 1.8 and 2.8 gigahertz, basically. And for one steerer position, so a fixed steerer position, for example, 0 degrees, you have something that looks like an average that is smooth plus reflection around it, fluctuations. Indeed, the S11 that you measure in the reverberation chamber is the addition of the free space component, that is something that is smooth like this, and the steered component. It means the part due to the RC backscattering, reverberation chamber backscattering. So the waves that goes to the wall and reflect back to the antenna. And this make fluctuations like this around the mean value. Okay, now I say, okay, I will perform the steering process, the mechanical steering process, so over steerer rotation. And this is what I obtain. So if I average the S11 over a steerer position, here it's 72 positions, then I can see that it's almost the same mean value. However, the fluctuations are much smaller than previously. Indeed, like it reduces the fluctuations around the mean value thanks to the steering. I can perform now a second type of steering, which is called the frequency steering. It consists in averaging the S11 over a very small frequency band, so that you consider it doesn't vary much in this frequency band, but the frequency points are all uncorrelated one to another, so you get something that you can average over it. So it's frequency steering. It's not cheating, as the S11 is not changing so much from one point to another. And if you do that, you can see here that you get something very smooth. Okay, and if you compare this to anechoic chamber measurements, which is the curve in black here, you can see it's very similar. So indeed, if you do a nice averaging of the S11 in reverberation chamber, you actually converge to the S11 that you could measure in free space. In other words, it means that the steered component of the S11, so the steered component is once you subtract the mean value, so the free space component, this steered component on average is equal to 0. Okay, so it means the S11 follow a Gaussian distribution that is centered so that its mean is 0. Okay, so this is the main statistical properties that we need in the reverberation chamber. So all measurements are based on that. Okay, so how do we measure it? The original approach was the substitution approach. The idea is to measure the power received by a reference antenna. So by reference antenna, I mean an antenna with a known efficiency from datasheet or another measurement kind. So you excite the cavity with port 1, you receive the power at the reference antenna on port 2, and you got the reference power, average always over the stereo rotation to get your field uniformity. Now you perform a second measurement by substituting the reference antenna by the AUT, and you compute again the received power on average. And as an ideal antenna would receive the same amount of power, whatever the kind of antenna, an ideal one would, for one particular RC, would receive the same power. So if you don't measure the same power, it means that the radiation efficiency of one of them is different than the other. And so the ratio between the reference radiation efficiency and the IUT radiation efficiency is equal to the ratio of the received power. So you know everything but the radiation efficiency of AUT, so you can compute it. So that's what has been introduced in 2004. It was the first time that radiation efficiency measurements have been performed in reverberation chamber. So this is very nice, but it needs a reference antenna. It's not always very easy to get a reference antenna when you are exactly sure about the radiation efficiency. And so more recently, in 2012, Chris Holloway proposed another method that doesn't need a reference antenna. It means you can perform an absolute measurement of the radiation efficiency thanks to this method. So I will develop it a little bit here because this is the one that I used then in the technical part. So the idea is to compute the ratio between the frequency domain and the time domain Q factors. Okay, so the total efficiency. So if you know the reflection coefficient, you can deduce the radiation efficiency. This total efficiency is defined as the square root of the frequency domain Q factor over the time domain Q factor. So what are these two Q factors? The frequency domain Q factors is defined this way. So this is related to RC constant. V is the volume, lambda, the wavelength. EB is the enhanced backscatter coefficient. So it's ideally equal to 2, and it allows you to evaluate the statistical properties of the RC, of your RC. Okay, so it's something that you can compute. Here's the EB equation. And here is the average of the steered component modulus squared of the S11. Okay, so this is somehow related to the received power by the antenna 1. And so the frequency domain Q factor takes into account the losses of the antenna. Okay, something that you measure the losses within the cavity, but the antenna losses are taken into account in this one. Okay, due to the S11. It's based on the S11 measurements. So you will feel or measure the Q factor through one antenna, and so it will take into account its losses. Okay, so it's different. The Q of frequency domain Q factor will be different from antenna 1 to antenna 2. However, if you look at the time domain Q factor, it is defined as omega, so the angular frequency, times tau RC, which is the RC decay time. And the RC decay time is the decay, the decaying time of the RC, of the energy within the RC. So basically here, if you compute the power delay profile, you take the S21 in the frequency domain that you measure between the two antennas. You perform an inverse Fourier transform of it, so you get back into the time domain. You do the modulus squared to get energy, and you average over it. When you look at this power delay profile, there is a first area here from t equals 0 to very early time, where it's not linear at all in dB, due to the antenna behavior that is very strong, like the losses due to the antenna at the beginning are very strong. And then there is a linear part here when the field is established within the cavity, where the energy is linearly in logarithmic scale, decaying as a function of time. And this slope is actually the director coefficient is 1/2RC. So 2RC here is defined as the inverse of the slope of the decaying time of a chamber. And the hypothesis of this time domain Q factor is that it does not depend on antenna losses. Indeed, the antenna are present into the reverberation chamber, but when you measure only the decaying time, then the impact of the losses of antenna is very small on this part of time. Okay, most of the antenna losses will occur at early time. So there is one Q factor that is not related to that is related to the antenna itself, so the frequency domain 1, and the time domain Q factor that is not related to it. And so when you do the comparison between the two, the ratio between the two, then it gives you the radiation efficiency. Okay, the difference of estimation between these two Q factor is related to the efficiency of the antenna, total efficiency that then you can from which you can deduce the radiation efficiency afterwards. Okay, so that's very interesting method that has been proposed by Holloway in 2012, and that's the one we are currently using to characterize antenna. And okay, so based on that, I will now talk a little about one specific technical study that we made to highlight how the steering effects will degrade or not the radiation efficiency measurements. Okay, so we know that the field has to be well steered within the cavity, but we will see how it will impact if it's not well done, the actual estimated radiation efficiency. So for that, we did comparative measurements. So we took the two same antenna, so patch antenna, the one that I showed earlier for the S11 results, and a classical log periodic antenna. So we take these two antenna that we put once in the APSYM reverberation chamber and once in the IETR reverberation chamber. So the IETR one is much bigger, about 5 times the volume. So the lowest usable frequency, the frequency starting from which the field are supposed to be quite idle, like the distributions could be quite good, so this frequency is lower for IETR because the volume is bigger. And also the uncorrelated stereo positions are much higher in the RC on the right. Okay, so this is due to a very large, like a larger metallic stereo. Like the mode stereo is much bigger, like in size, so it will give more correlated stereo position. Okay, so we perform the measurements. So we look only at the patch antenna results. We perform measurements within the two chamber, so trying to do the exact same kind of measurements, but in two different reverberation chambers. So if we look at the S11, the two are very coherent, very similar. Of course, the mean value is almost the same, but the fluctuations depends on the RC itself, so that makes sense. And it's very close to a simulation of the antenna. Okay, but now, if we look at the radiation efficiency, we see there is quite big difference. So first, the simulation is overestimated, or at least is higher than the two measurements. The general shape, however, is almost the same. But more importantly, the measurements within IETR and APSYM RC is quite different. It's about 5 or almost 10% on average difference. And so, okay, it might be due to uncertainties, right? There is always uncertainties, maybe 5 or 10% could actually go within the uncertainties budget. But still, we wanted to investigate why such a difference. So this is the radiation efficiency equation that we used from the one I introduced you earlier. There is the Q in time domain. There is the Q in frequency domain, which is all the this part here. And there is the matching that is taken into account. So this is the equation introduced by Christopher Holloway to measure the efficiency. Okay, so starting on that, we wanted to investigate where does this difference come from? Okay, there is a Q factor that would be different, but the steered component should be different as well. So where does the difference come from? So to do that, we actually compute 4 different terms. So the EB, the volume over the Q factor, the steered component of the S11, and the matching. So it's named 1, 2, 3, and 4. And we perform the ratio between this, for example, the parameter number 1, measured in APSYM, divided by the one measured in IETR. Okay, so we perform the ratio of these 4 components between the 2 RCs. So if I start with 3 and 4, so we look at EB and the matching, the ratio is close to 1. So basically, from one chamber to another, it's almost the same thing. It's very close to 1. So the difference doesn't come from this. Now, if we look at the red curve, the Q factor, we can see that there is quite a difference. And this is straightforward as the 2 RCs are different. So the Q factor is much higher in the one in IETR. So, of course, there is a change here on the red curve. But however, this change is not compensated by the change in the blue one. Indeed, if the Q factor is smaller in one RC, then the steered component should be smaller too. And this is not what you observe here. Okay, so as expected, there is different Q factors, but same steered component level. So that we try to investigate why the steered component didn't change. So for that, we did a very small statistical study where we model the steered component. It is based on the S11 minus the average of S11. So we did here the same. We take X as an average value plus a noise. So these are random variables for imaginary and real part of the noise. So Gaussian center distributions, and as in RC. Then we compute S as X minus X average, a mean value of X. Okay. And if we look at that, so if we take only, if we take only 10 samples, for example, here we take 10 samples of our distribution and we compute the mean value of this. You can see here that the 0 value that we impose, like the noise should be center distribution. So the mean value should be 0 too. It's not 0 here because it's not very well estimated due to a limited sample size. However, if you took a large one, then the mean value is better estimated due to the large sample size. So that makes sense, of course. But then what we observe is that once we compute, so I'll go quite quick on this one, but once we compute the average value as a function of the number of samples, then we actually see that when you have a limited sample size, for example, 10 here, you always underestimate your mean value. It means that not only you misestimate it, but you always underestimate it. And if you underestimate it, then you will underestimate the radiation efficiency in the end. So you get something different from one reverberation to another. But if you have a limited sample size, so with limited number of uncorrelation superposition, you will systematically underestimate your efficiency. You will not misestimate it with either higher value or lower value. You will systematically underestimate it. So that's the main point that I wanted to stress here. And to highlight this, to see that it is only due to the estimation of the mean value of a reflection coefficient. We see 2 aspects to overcome this. So for example, here, so these are the results in 4 different cases. There is always a simulation as a reference. Otherwise, APSYM, if you do the mechanical steerer only in green, you get this curve. And if you perform the frequency steering, then the radiation efficiency will strongly increase. And it actually gets the same thing in IETR, where even though the mechanical steering is quite good, if you add some frequency steering, it will overall increase your efficiency. Of course, it won't increase forever, but it goes closer to actually the good value of efficiency. So it's very important to actually perform steering, well-performed steering. Another way to see it is like we perform source steering. Source steering is a modification of a position of AUT. So the AUT received a certain amount of power, then you change the location, and we say that the power should be the same, thanks to the spatial uniformity. So we do that, but still it lacks moving the antenna is equivalent to moving the steerer. So you get another field distribution, and you can perform average on it. So we did it 5 times, so 5 different source steering, and for each AUT position, we perform mechanical steering. So for each configuration here, there is 72 measurements, and then we perform 5 times 72 on average. So what is interesting is that, when you do the 5 source steering, you always estimate the radiation efficiency on the same way. So it's very repeatable, as whatever the source position, you get the same thing. So it makes confidence about the results, right? But actually, when you use all these measurements to compute the average of the S11, so not only for each configuration separately, if you do the average on all of them, then you get this curve in black. Okay, so you could think at first impressed that you would get something in average among all these curves, but actually you will strongly improve your radiation efficiency estimation, and it will strongly increase in this case. Okay, so it's very repeatable, but if you don't have enough uncorrelated samples, you will do systematic underestimation. Okay, so I got 1 minute left. This is my conclusion now. So what I wanted to stress is that radiation efficiency is a critical parameter for miniature antennas because of a classical trade-off between size, bandwidth, and efficiency. Reverberation chambers are very convenient to measure it because you don't need to rotate the antenna. You always take into account all the incident power that come from all directions without rotation. But you need to have a strong, like a lot of uncorrelated zero positions in order to get accurate estimation of a radiation efficiency. Otherwise, you will systematically underestimate it. And as perspectives, we are currently doing some contactless measurements within RC, like in order to avoid the feeding cables that goes on the antenna that can disturb the radiation efficiency that you measure. If you deal with miniature antennas, then the setup with cables can actually disturb the radiation performances. And so to avoid that, we are trying to do contactless measurements. Means that you have 2 antennas that are measuring a transmission coefficient, and the AUT are here and unconnected to any instrument. And from the transmission coefficient between the 2 horn antennas, you can actually deduce the radiation efficiency on these 2. So hopefully 2 years from now at APSYM 2022, we will talk more about that. Okay, for 5 minutes, I'll stop here. Thank you very much for your attention, and I'm okay for questions if you have some.
Thank you, sir. There are some queries in the chat box. Can I read out?
Yeah, sure. I will check also.
So first question is, how important is cable shielding with aluminum foil? Is it dependent on frequency of operation?
How important is cable shielding with aluminum foils? I'm not sure. Important for what actually? For Schreier-Meinen? Like cable shielding is important for, what do you mean? For the, sorry, I don't get exactly the question regarding the radiation efficiency. Cable interference. Okay, this is not something I've been interested in. Actually, it's more EMC characterization. So of course, reverberation chamber has been first used in electromagnetic compatibility, especially for this kind of application, for example, to perform cable shielding and how good is it. But regarding my experience in radiation efficiency measurements, I always neglect that. Like I suppose that I don't have any interference regarding this in my case. And I think it's quite true, but I didn't perform any EMC measurements regarding what I'm doing. Okay. Okay, so if I go up to what frequency range are reverberation chambers generally used? Fact is, it starts wells starting from one frequency. It means that below the lowest usable frequency, there is not enough modes that will resonate within the cavity, and so the spectral and spatial uniformity will not be reached. So we usually talk about the lowest usable frequency. But then, of course, when you go too high in frequency, I don't know, after 10 giga or something, then the losses will be very, very high. And it's not always very easy to deal with it. And so you can, of course, do some miniature reverberation measurements. For example, there is some measurements in 60 gigahertz that I see in IETR, actually, especially. There is one dedicated reverberation chamber for 60 gigahertz. I'm not sure about anything higher than that for now. And it might be tricky to deal with the losses at these frequencies. But yeah, let's say for now it goes from let's say 100 megahertz to 60 gigahertz at least, to my knowledge. Okay, on what factor of the design of stirrer dependent is it simulated in some EM computational tool? Yeah, actually the stirrer, the mode stirrer design is one topic on research. It's not really ongoing now. I would say it was more the case like 20 or 30 years ago. Let's say that now any complex shape stirrer would do it quite good. So you have to do something that has no symmetry, less symmetry. It has to be the bigger as big as possible. But also, if you do it big, then it will reduce the size that you have for your measurements. So it's always a trade-off between the two of them. But yeah, there is some simulated case, like you can do it on simulation. Sometimes we measure the diffuse cross-section, like the scattering cross-section of the stirrer, and the mode stirrer performances are related to the scattering performance of a stirrer. So the more it actually diffuse the field, the better will be the stirrer. So sometimes it is studied this way. Any books for further reading? There is some books for reverberation chamber. So there is one like the David Hill one. So David Hill, I don't know when, maybe 2000, 2010, he did a book on reverberation chamber, which is very complete but theoretical. And I know that from Liverpool, Kian Shu did a book also that compare anechoic chamber and reverberation chamber for antenna measurements. So it's more dedicated to our field, and it's quite interesting as well. Okay, can reverberation chamber be used informative? Sorry, do you have to stop or just the last question if I answer quickly? Can reverberation chamber be used to measure radiation pattern? Well, it's actually possible. We have some measurements ongoing to perform radar cross-section measurements, and from this to deduce the radiation pattern. So there is already some stuff to measure the radiation the radiation pattern. So the idea is to extract the ballistic wave or the direct path between the antenna and the antenna on the test from the diffuse field within the cavity. So it's not very straightforward to perform, but actually it works. So there is some methods with that measure the Doppler effects. There is a method based on the Raysian K factor to measure the direct path, and we are developing a method based on radar cross-section measurements, something that I present actually 2 years ago, part of it. But yeah, it's possible. It's not straightforward yet, but it's possible, and hopefully we can soon do anything that you perform in anechoic chamber. We'll be able to do it in reverberation chamber. Okay, question first one. Is there any differences in?
Any question, if it is there, you can directly ask also.
Okay, is there any difference in radiation efficiency results between classical gain-based method and reverberation chamber-based method? Yeah, actually, so the question is about differences between the two ways of measuring it. Yeah, there is differences. Of course, I didn't perform yet like extensive comparisons between the two methods. I would say that for for most antenna, it will get the same results. Always, it depends on the radiation pattern of your antenna at first. If you get like with reverberation chamber, it takes into account all directions at the same time. However, if you do anechoic chambers, you will be limited by the number of cut planes that you use. So depending on the shape of the radiation pattern that you have, you might have something that is much less accurate in anechoic chamber. But of course, the process in anechoic chamber is well mastered, so it works still well. But I would say that if you master well the behavior of your reverberation chamber, you will get some more accurate measurements. And it's quite also easy to evaluate the uncertainties as they are based on the statistical properties, and there are indicators on that. What about comparing with reverberation chamber with Wheeler cap method? Yeah, actually, Wheeler cap, I didn't have time to mention it as well, it was too short. But Wheeler cap is interesting as it is very simple to implement. Compared to reverberation chamber, they are both based on S11 measurements, very easy to perform. However, Wheeler cap, you actually avoid radiation. So you kill the radiation and you suppose that you are measuring only the loss impedance of the antenna. In reverberation chamber, you make the antenna freely irradiates and you measure received power. There are some papers, especially from Gwen Lefur at IETR, that compare the two of them. Let's say that if you do it well, you would get some very similar results. However, the uncertainties are very difficult to compute for Wheeler cap methods. Or you will need to do some steering as well. Then you move the antenna within the Wheeler cap, or you add some reflector within the Wheeler cap. So once you want to give something more accurate, I would say Wheeler cap might be a bit tricky. Like everyone likes to try it, but then in the end, you're never sure about the result that you get. So I experienced it a little bit, and I'm not convinced by
there is no further question.
Okay.
Okay.
I mean, is it time anyway?
Thank you, Dr. Francois Sarrazin, for in fact, the accurate estimation of antenna radiation efficiency has been a hot topic for many years. And you have very beautifully explained in your presentation how it can be done within a reverberation chamber. I'm sure most of the participants who attend the talk got benefited. Thank you, Dr. Francois Sarrazin, for the nice presentation. And it was very informative and sharing your experience and time with us today. Thank you.
Well, thank you all. Thank you for the chairman for the QV organization, and hope to attend 2 years from now and in Cochin for sure. Well, have a great day. Thank you, everyone.
Thank you, sir. It will be a great pleasure for us to listen to you again. It was an informative session.
Now we are entering into the first technical session of today, which is based on antennas. There are 5 paper presentations in this session.